We will now continue with another important aspect of cloud-based software, which is multi-tenant architecture. Here, let us understand how multi-tenancy is actually implemented, and how one can really build a platform and which can support multiple types of customers. So the need for multi-tenancy was actually not was existing long before the SaaS platform or the SaaS or cloud came into picture. It was there for a long time. So for example, let's look at the banking application, a bank with many branches. So typically, if you look into a banking software, you'll find that each branch had a requirement that they should be able to access only its own data. But the bank may want to apply some global changes by adding a field to the master table, and that should be accessible to all the branches. Now, a branch can also add specific fields which is only applicable for that particular branch. That's a local branch specific data. So while on one hand I should be able to add local branch specific data, on the other hand, at a bank level, some global changes should also be possible. Global processing like interbank reconciliation should be possible, and sometimes fine-grained data-centric access policies can be implemented. For example, high-valued transactions should be visible only to the special people in the bank. Special customer names should be invisible by default. So such things are data-centric access that could be another requirement. Now these are, in a sense, requirements for multi-tenancy. These are essentially, in a sense, need to be if they have to be implemented, then multi-tenancy, the notion of multi-tenancy need to be implemented. Now today's multi-tenant systems exactly implement such things. So if you look at the multi-tenancy or multi-tenant features of popular SaaS applications, you'll find exactly these kind of things are actually there. So today multi-tenancy is synonymous to the hosted software as a service applications. Essentially one code base and used by multiple clients, possibly multiple corporates, multiple organizations, multiple customers. So when we're dealing with multi-tenancy, that example that I gave, that bank, now what could happen is that one could host banking as a service, which will have the banking platform, and suppose that there are 5 banks who basically don't have the IT infrastructure or the required capability to implement their own banking solution. So they can basically buy this banking as a service. So, but each of these bank will have their own requirement, and they might come to this service provider for the implementation. So such an approach essentially is quite profitable for both the service provider as well as for the end customers. Basically, it is economies of scale that drives down the cost. To buy that service, it will be far cheaper compared to building it. Rapid and invisible upgrades are possible because the service provider will take care of that. So pictorially it might look like this. There is a single code base today, and there is a SaaS product. There is a configuration data, and in fact there are configuration data for each customers. And in this picture you see that there are three customers, customer A, B, and C, and each customer has its own application data and its own configuration data, and they are isolated. Now each customer can configure the product according to their requirement. So the way it can be implemented is either a single data store or maybe multiple data store. In this example, it could be a single data store. So let us look at a single data store, a single schema model, which is the simplest one to implement multi-tenancy. So a single schema model might look like this. So this is a table which contains different fields, but most important is that there is something called multi-tenancy ID or OU ID. OU stands for organization unit, OU ID. And you see that each row corresponds to a particular organization. For example, in this case, there are first three rows correspond to first organization. So, and the last two rows correspond to the second organization. So there is an extra column which is OU underscore ID that indicates the organization ID. Each query that's fired is modified, and each query is appended with OU underscore ID filter. So a query that's coming from customer A will be appended with a OU ID filter. Now this has a problem, though it is simple to implement. The problem is that re-engineering an existing application using single schema model is not that easy. If there is already an application and you need to now make it a multi-tenant model, then such a re-engineering would be quite difficult if a single schema model is adopted. Another problem is that it is difficult to have customer specific extensions. One need to really implement additional metadata table to handle in the application. Essentially that metadata table need to be created, and application need to be aware of that metadata table, and that need to be used for additional extensions. Example is this, that suppose there is a single schema. Well, we'll go with the single schema model. I have got name, address, value, and let's assume that this is a GUI. So here in the GUI, suppose I just supply the name, customer name, and then I click this button and assume that this particular GUI is for a particular organization. So this organization ID is also known. So there is organization 1. So this organization 1 supplies a particular customer name and clicks this button. Then what happens is that it basically fetches the common data, which is name, address, and value, from the main customer table. So suppose that the customer ID or the organization ID is 503. In that case, it is going to fetch these two, assuming that the customer name remains the same. However, if the customer names are different, then essentially it might just select this particular row with OU underscore ID is equal to 503. So understand that this is a common table for different customers. So first and the third one is for one customer, the second one is for the second customer, the second row. Now what about these two additional attributes, hobby and birthday? Now this is a common one. So obviously this is fetched and this is returned, but there will be additional table, customer fields table, and this is how it can be implemented. So the first column is entity, and then this is the field, hobby field, this is a birthday field, this is a risk field. So let's look at this. So for the organization 503, the organization 503 wants additional attributes like hobby and birthday. However, organization 490 wants only risk, but organization 490 does not require hobby or birthday. So this particular UI is for 503. So how will it know? How will the software know that what are the additional fields that need to be fetched? Well, it is based on this OUID. So when this OUID is supplied, it fetches the common attributes. Then it goes to the additional field table, and then what it does is it uses this ID again, and using that ID it knows that these are the extra attributes, hobby and birthday, and then these hobby and birthdays are essentially fetched. So it becomes a kind of a complicated join, like suppose that the customer is 100. In that case, or suppose the customer is 102, let us say. So this one's for this customer 102, name, address and value are copied here, and then this 102 is used here along with 503, which is organization ID, and then it fetches additional fields like hobby and birthday, which is tennis and this is a birthday, and they're populated here. This is how essentially this query will be implemented. So the first is common field and then fetch custom fields. Any update will require updation in both the tables. Let's look at the multi-schema model. Here application computes the OUID and then switches to the appropriate database. Each schema for each customer. So for example, one customer type can have name, address, hobby, birthday. Another customer can have a name, address and risk. So there are separate metadata table for customization. Therefore this field name and field value pair is not necessary in this case. So just customization information is good enough. Let's look at the same example again. Name, address, value, hobby and birthday. So this is the OUID and these are the custom fields, hobby, birthday and risk. So fetch customer with a particular name and then OU, and then essentially it first comes here, and then basically what happens is that it goes to an appropriate table, customer schema for 503. If suppose the OUID is 503, then it actually comes here, and all the data like name, address, hobby, birthday, value, all of them are fetched here. Now this is basically the metadata field, which is or metadata table, which is changed if this metadata is modified. Similarly for customer schema, this is another completely separate table. Update would essentially update only one table here, not this. So multi-tenancy using the cloud data store is another interesting option. Google App Engine would support the multi-tenancy anyway. So for example, Google App Engine will ensure that user 1's data store does not interfere with user 2, though the underlying data structure for user 1 and user 2 might be the same. So suppose you as an application developer, you want to implement your own multi-tenancy on top of Google App Engine. For example, you can create a customer kind. Once you create a customer kind, you really cannot create it again. So what you can do is that you can basically leverage the dynamic schema property of Google file system to support such things. Example is that once you create so what the problem is that here, if you create customer kind. Kind is a terminology that's used in Google App Engine. Now once you create customer kind, you can't create it again, meaning that you can't create a different customer like 503 or 490. One customer kind and that's it. But how do you then implement various multi-tenancy feature if you're using Google App Engine as underlying data store? So Google File System basically supports this dynamic schema. So what one can do is that you could basically create different subclasses of a customer, like customer 503 or customer 490. These are the two different subclasses of customer. They can be created, and one can use interesting programming language level features to basically implement such multi-tenancy feature. For example, if you are implementing a program using Python, for example, then at runtime you can basically create a class using the type function, and this becomes a quite handy function to really implement client specific or organization specific customizations. For example, you can start with a clean customer kind having possibly basic data set, but let us say you can dynamically create subclasses of customer type. Say for example customer underscore 503 or customer underscore 490 using this type function, and you can create this kind of schema for customer 503. You can create this kind of schema for customer 490, and then these schema can be used for storing values related to the organization 503, or this schema can be used to store the values related to the organization 490. Well, this is quite Google App Engine specific. The reason why I brought this is to just show that if you are using such platform as a service feature from Google or any other service provider, then how smartly you can build your SaaS application where you can implement this multi-tenancy feature. So that's the reason why I brought the topic, that suppose you want to build a SaaS application using, let's say, Google's platform as a service feature, then this could be a nice trick that can be used to basically implement a multi-tenant application.